now time for our final speaker, who will be Lars Mattson, who will be talking about interstellar dust in evolving 3D supernova shockwaves.
We're using something called a pencil code. I don't have time to describe the details about it, but what we do is 3D hydrodynamics with Lagrangian particles simulating a shock wave into homogeneous medium, basically. If you want to know more about the pencil code, it's freely available on this GitHub site, by the way, and there's also a lot of more information about the code there. So, there are a few questions you could ask, and particularly two questions. One is, can the pre-existing dust in the ISM survive the passage of a blast wave? And now we're talking about a different scale here. So there's this late stage supernova remnant we're talking about. And the short answer is yes, if the grains are large enough. And I think we already heard that. Especially when it comes to sputtering, large grains tend to survive, while small grains are sputtered away. But it's also depending a little bit on if the grains are decoupling from the gas or not. And there was 1D simulations tend to say that you have the grains ending up in front of the shock or being thrown forward, basically, reflected. And another thing you can ask is, will a 3D supernova shock behave any differently compared to a spherical or symmetric thing? And, well, again, the short answer is yes. You will have instabilities and stuff. And it will break up and will look quite beautiful, in fact. But another thing is also, it's quite unclear what happens to the dust grains in this case. Are they actually affected by the instabilities or not? So that's what I've been studying here. And when we talk about instabilities, there are basically three instabilities that are dominating here. One is the thin shell instability, which was also known as the Vishnlac-Ostriker overstability, which I think is a better name for it. There's the Rayliegh-Taylor that you all know about, and then there's possibly a third one, and we're not sure about this yet, but there's something called the Richtmyer-Meshkov instability, which might occur in this case. To review a little bit here, the Vishnlac-Ostriker overstability is something that causes a wiggliness of the thin shell as it expands. We have seen this in previous simulations, earlier simulations at low resolution. You get this wiggliness. If you can look here, for example, you see this wiggliness in the shell, which is basically this Vishnlac-Ostriker thing. And the hypothesis I had was that if you get this, you can induce other instabilities, and we will see that in a minute. The Rayliegh-Taylor instability is something you might have remember from something caused by the reverse shock when you have a contact discontinuity between the ejecta and the CSM, and then you have a reverse shock passing through it, and you get mushrooms, basically. Then there's another way of getting mushrooms, and that's the Richtmyer-Meshkov instability. So if you have an interface between two fluids of different densities, and you can picture that it's kind of something like that you have here in supernova, or with a blast wave. And then when a shock passes through this interface, you will get mushrooms. Now, we also had dust. We have, I don't know, about 10 million Lagrangian particles in the simulation. So the dynamics of these particles is basically due to the forces acting upon the particles. And in principle, we have three types of forces here. We have the kinetic force, which is basically gas particles hitting the grains. And we have the plasma drag, which is something that is induced because by Coulomb forces, because the gas is ionized. And then we could also have magnetic field effects. But I have the magnetic module switched off in the simulations at this stage. We'll probably try that in the future, by the way. So we have two forces then. Obviously, the magnetic forces are irrelevant here. The kinetic force is also obviously going to be important. The question is, will the plasma drag be important? And yeah, the math is a bit ugly. And we tried to implement this, and what we came up with in the end is that, yeah, if you have small grains, then they have this parameter called psi here, phi, which tells us that if you have small grains and not too large temperatures, then yes, you will have effects. But if you have large grains, and what we're simulating here is pretty large grains, something like a micron across, and we have quite high temperatures. So this effect turned out to be quite small. So it's basically what you see is mostly kinetic drag, in fact. So here's then a simulation of a blast wave into homogeneous ISM. And this is for relatively low density. And to the left you have the gas, and to the right you have the dust. And as you can see, they have some diffusion in the beginning, and not much breakup, a little bit at the ends maybe. But most of all, the gas and the dust seem to follow each other. So there's no clear decoupling here. If we increase the density a little bit, more interesting things start to happen. First of all, you see here this Vishnlac-Ostriker instability forming here now. You can see this wiggliness here, which seems to be inducing more instabilities, and then everything just breaks up. And if you go to even higher densities of the medium, you will see this at an earlier stage, and the breakup is more prominent, I would say. So the question is then, is there really no effect on dust here? Well, if we look at the dust-to-gas ratio, you can notice that you get an over-density in front of the shell, and a sort of under-density at the shell, which is something that is going to be quite important, for example, for sputtering, because where most of the sputtering is happening is where you have the density peak here in the gas, of course. And the grains ending up in front here are probably surviving. Then we also started making simulations in very high resolution. And then you can see all these beautiful tiny details forming here in the shell. But if you compare them with the dust distribution, it doesn't seem to do very much of any interest. So I think one can do small, lower resolution simulations and still get quite accurate results, I think. Now, to explain a little bit what is going on here, there's some kind of decoupling here, but why is there? What is the criterion for having decoupling? And it's basically if you have a shock or a shell that's expanding, it has a certain thickness and it has a certain speed. And from this, you get a time scale. This time scale you should compare to the stopping time in the drag force equation. So the criterion for having decoupling is, of course, or coupling, I guess, is that the stopping time should be much less than this time, the shock passage time. So what we have is something in between. You get quite a lot of coupling, but not perfect coupling, it seems, for these grain sizes. If you go to very small grains, you will have perfect coupling. If you get to very large grains, I would say like 10 microns or something, which is unrealistic, then you see more decoupling. I could in principle show you that, but I don't have it here in my slides. So what would then be the continuation of this project? Well, it would of course be interesting to look at propagation into an inhomogeneous medium. And especially as you saw that increasing the density of the medium was also affecting what's happening in terms of instabilities. So if you have an inhomogeneous medium with dense clumps, or relatively dense clumps, not quite as dense as the one clumps we heard about in the last talk. Things will be completely different, I'm pretty sure. Adding magnetic fields will also change the picture. Thank you. And maybe there can also be self-gravity effects, because if you calculate the Jeans wavelength for this problem, it turns out that the lumps, the structures that you form in the expanding shell is of that order. So you could, in principle, have self-gravity effects that could play a role. And then again, what I haven't been doing is I haven't calculated the sputtering rates or dust destruction in any kind of way. And that is partly because we haven't done all the other things yet, but also because doing this in 3D is extremely expensive. So we want to try the simpler things first, of course. So, preliminary conclusions then. This is an ongoing project, so this is just a progress report, basically. Well, to wrap it up, you could say that the tight coupling approximation that sometimes is sometimes being used is probably not so good, and we saw that already in the previous talk. Another thing is that the separation of gas and dust increases in denser environments, and therefore clumpiness is an interesting thing to explore. And also, also an inhomogeneous medium will have initial dust to gas separation, which is something which is quite important in this case, because what I've shown you were simulations where we have a homogeneous mix of gas and dust, and then a blast wave expanding in it. But if you already have separation between gas and dust, and when you start, you will have a completely different scenario. So I hope to return with new simulations at some point where we investigate the inhomogeneous case also. Thank you.
Thank you. Any questions for Lars? No?
So if the thing is saying that big grains can get like pushed away basically from the sputtering stuff,
yeah,
and also
repeatedly kicked.
Yeah, and also they've got most of the mass in the interstellar medium. Is that going to imply that supernovae don't destroy dust grains that efficiently? I mean, in the interstellar pre-existing dust grains.
It's difficult to give a straight answer, but I think if you sort of extrapolate from what you saw here, the destruction efficiency, there is a limit to the efficiency, definitely. Where the limit is, I don't know, but sure.
Any other questions? So I have one possibly slightly strange question.
Okay.
I was thinking about we haven't talked actually much at all today about the geometry of the actual grains themselves. Yes. I'm assuming these are sort of modeled just as points or spheres. If we were to consider fluffy grains or porous grains or ones with much more interesting geometries, the shapes of the grains themselves, would that affect the results significantly, or?
Good question. Yes, to some extent, yes. Especially when you model the destruction. I think it's very important what kind of shape the grains are. I'm not sure about drag forces and the dynamics here, whether that actually matters that much. I think it's mostly the mass of the grain that is. Okay,
any other questions? Okay, let's thank Lars again.